To understand how a real-world transformer behaves, engineers use a model like this, called an equivalent circuit. But in an AC system, the voltages and currents aren't always in sync. To see the full picture of how they all relate, we need a special kind of drawing, a phasor diagram. Let's build this diagram piece by piece. The most logical place to start is at the end, the voltage being delivered to the load. We'll call this V'2, the secondary voltage referred to the primary side. Since we can orient our drawing any way we want, let's place this vector horizontally as our reference. Now our transformer is powering a load, maybe a motor. Most of these loads are inductive, which means the current naturally lags behind the voltage. So we'll draw the load current, I'2, lagging V'2 by an angle we'll call θ2. The voltage actually generated inside the transformer isn't what the load sees. First, we lose a bit of voltage simply because the copper wire of the secondary winding has resistance. This voltage drop, I'2 times R'2, is always perfectly in phase with the current causing it. Next, not all of the magnetic field created is useful. Some of it leaks and doesn't link with the other coil. This leakage acts like a small inductor. A voltage drop across an inductor always leads the current by 90 degrees. So, if we add these lost voltage drops back to our terminal voltage V'2, we discover the voltage that was truly induced inside the winding by the magnetic field. We'll call this E1. This is the internal electromotive force. Now, let's think about what it takes to create that E1 voltage in the first place. Even with no load, the transformer needs to draw a little current. Part of this is the magnetizing current. IM. The physics of induction dictates that the induced voltage, E1, leads this magnetizing current by 90 degrees. The other part of the no-load current accounts for energy lost as heat in the iron core. We model this as a resistive loss. This core loss current, IC, is therefore in phase with the voltage E1 that drives it. The total current the transformer draws when idle, the no-load current I0, is simply the vector sum of the magnetizing and core loss currents. So, what is the total current being pulled from the supply on the primary side? It has to do two jobs: provide the current for the load, I'2, and provide the transformer's own no-load current, I0. The total primary current, I1, is the vector sum of these two. We're on the home stretch. But we have to account for the imperfections on the primary side, too. Just like the secondary, the primary winding has resistance which causes a voltage drop, I1R1, that's in phase with the primary current. And finally, the primary winding has its own leakage flux, creating an inductive drop, I1XL1, that leads the primary current by 90 degrees. This grand sum, all the way from the origin to the tip of the last voltage drop, gives us our answer. This is V1, the voltage we must apply to the primary terminals to make everything else happen. And there it is, the complete phasor diagram. It might look complex, but by building it one step at a time, we can see the beautiful, intricate dance between all the voltages and currents. It tells the full story of how a real transformer works.